So here we have two pendulums. These are just a ball bearing in a little bit of a t-shirt that's cinched with a knot here. And each of them have two strings that go up to the ceiling like that, so that they only swing in one plane. They're not going to swing this way very much without loosening one of these things. And so it just swings like that. Just a pendulum, nothing complicated. I made it so it's stuck to the ceiling using binder clips because the drop ceilings in Geo4 and Geo6 work with this, but if we wanted it to be portable, it would need a different kind of frame. And this is supposed to be a demonstration of coupled pendulums. But right now they're not coupled. They don't have to talk to each other. Maybe a very slight bit because they're attached to that same little swingy bit of the binder clip, but probably not. I haven't noticed any coupling. One important thing is to get their frequencies the same. The frequency of the pendulum only depends on the acceleration of gravity, which we can't change, and the length, which we can. And here I've used a midshipman's hitch so that you can change the length of these. You just sort of pull this knot up or down, and it changes the length of that string. The other way to do it is to move the clips in and out, which will change the length of the string. So to check that they're the same length, I pull them up and I let them go at the same time. Then I wait several swings, and if I get over on this angle, I can see which one is leading or lagging. The one that's leading has the shorter string, the faster frequency, and I think it's this one right here. The one that's closer to me is going a little bit ahead of the other one. So I want to make that one's string a little bit longer. Probably the easiest way to do it is to move that a little bit over. And they don't have to be super exact. Like, these are already degenerate pendulums to within less than 1% of their frequency. So I'm just being a little bit perfectionist right now. It's not really necessary. So this is good enough, but they're not coupled. They can swing independently. You can leave one in place and swing the other. Nothing happens to this one. Stop it. And if you watch this for a while, it shouldn't, in principle, get coupled. So maybe a very, very tiny bit of coupling because of that, the swinging of that little guy up there. But it would take a long time to visualize that. The way you can couple them is you take another piece of string and you tie them together. And you could tie it at any height, but I found maybe a quarter to a third of the way down from the top seems to work well. And now you can get some cool behavior like beating. So here I'll hold one in place, move one of them, and in operation I have to sort of watch this knot, try to not let it wiggle, because actually introducing that knot now lets these things go side to side. It introduces an additional degree of freedom, which we don't really want, but with this setup there's no getting around it. So I'll pull one off and I let go. Through the coupling, the one that's moving starts moving the second one. And after some number of oscillations, this one stops moving. Right about here, stops moving. And now the situation reverses. This one starts giving its energy back to the first one. And at some point, this one will stop moving. Right about now, and we're back to where we started. And so it'll go back and forth like this. This is beating. If you look at the position of one of these as a function of time, it can be described as beating. This oscillation, but there's also an envelope that the beating envelope, which gets bigger. At this point, this one is getting bigger, and it'll reach some maximum, and then it'll get smaller again until it stops. This one's getting smaller, and now that envelope has come to 0, and then it will get bigger again. It would be better if I could draw this on a chalkboard. And so this is just with some arbitrary initial conditions. I could also start it, I don't know, I could give one of them a whack at time 0, and the same kind of thing will happen. And at some point, this one will stop. There, giving it a whack makes things do a little bit more crazy stuff because it gets a little bit of horizontal motion. It's probably not so great for demonstration purposes. And then the other thing that's important, that's relevant to the coupled oscillator chapter in the 332, the Physics 332 curriculum is normal modes. I can take both of these and pull them to the side at the same amount and let them go. And if I let it go correctly, which that was a little bit awkward, they will swing together, and it will just keep doing this forever until it runs out of energy. This situation is the first normal mode, and there's only one characteristic frequency here, and it turns out that it's the same as one of these pendulum by themselves, because now that they're swinging together, it doesn't matter, they're tied. That little knot's not really doing anything. Alternatively, the other normal mode, there's two oscillators, they're going to be two normal modes. That was the first. The second one is when they swing oppositely. It's a little bit harder to get this one to go. You have to look at the little knot up there, and as I pull one forward and one back, I try to keep the knot in the same place. I let go both at the same time, and now they'll swing back and forth. They're getting a little crazy with that knot swinging back and forth, but in principle, this is the other normal mode, and it has a different frequency than the first normal mode because now the coupling is important. And we did a measurement in class where I had the students use their phone stopwatch and we counted measured the time it takes to do 10 oscillations, both normal modes, calculated the frequency, and they're different by maybe 10%. Hard to tell just by looking at it that this is a higher frequency of the other one. So you can see that difference experimentally by just doing it in class, and everybody can participate, which is pretty cool. And the last thing is that this behavior, the beating behavior, is a superposition of those two normal modes. And the superposition of two frequencies that are not quite the same gives you beating. That's why you see beating of the oscillation of one of these things. If you just don't ignore the other one, just look at this one, it's exhibiting beating. And you can measure the beat frequency. So you have your students get their stopwatches ready, and when one of these things stops, like right now, everybody starts their stopwatch, and then you wait until it comes back to that same configuration where this one stops again, and that time is the beat period, and you 1 over that time is the beat frequency, and it turns out to be the difference in frequencies between the two normal modes. This is very cool, and it works to within 10%. You know, the measurements we were able to do in class reproduced that behavior to within 10% numerical accuracy. Really pretty good for a setup that costs nothing. Yeah, and that's basically everything.